Good evening, all. On behalf of Sophia College Physics Department, I welcome our guest, Professor Jasjeet Singh Bagla from Indian Institute of Science, Education and Research, Mohali, our respected principal, Dr. Sister Ananda Amrit Mahal, and all participants. Every coin has two sides. Due to pandemic, we are forced to go digital for all our activities. However, as opposed to offline oration, we have invited our guests from different parts of India and overseas. Also, we are getting enthusiastic participants from all corners, including our near and dear staff and students. 2020 Physics Nobel Prize was given to scientists who have worked on the most exotic phenomenon in the universe, the black holes. Today's guest speaker, Professor Bagla, will enlighten us on this topic. Now I invite our respected principal, Dr. Sister Ananda Amrit Mahal, to officially inaugurate Sophia Nobel Oration for academic year 2020-2021 and address the gathering. Over to you, sister.
Thank you so much, Dr. Saxena. It gives me great pleasure to launch this entire series of Sophia Nobel orations, especially since this particular year we have actually got experts in to give us some deeper understanding and insights into the award winning Nobel achievements in six different spheres in all the areas. It has been a great joy for us that this year we've been able to invite people from different disciplines to come in for this. The idea of the Nobel orations started 19 years ago, and I think Dr. Subramaniam is going to give us a little more of tracing of the way in which this entire initiative has developed. But the idea, and this is what I would like to emphasize, the idea is that we want students across the board, and a lot of us perhaps who are experts in our own area but not experts in other domains, to be acquainted with some of these achievements which occupy the rarefied space, air in outer space, as it were. The air there is very scanty, but it's also very exhilarating. And this is what we would like our students and the students and all others who may be coming in here to be acquainted in a manner in which we would be able to understand, access these very, very esoteric, exotic, as Meeta said, areas of pure science which are at the cutting edge of the domain, the discipline, and yet also very essential for us to understand so that we know something of what is going on in this wonderful area of the academic world and the world of science, literature, efforts towards peace, economics, etc., medicine as well. With this very brief introduction, I want to thank each one of you for being here today. Very special thank you, Sir Dr. Jagjit Singh Bagla from ISER Maholi, for taking the time and making this entire program a success for us. It's been so kind of you to find ways of explaining this to the ordinary lay people, to our students of physics, but also to students of literature like myself, who really have no clue about so much of it and yet are fascinated by the idea of the black hole. So, without too much more detail, I would like to invite you, sir, to be our expert guide through this labyrinth. Thank you so much for being here with us, and we launched this Nobel Oration series with the Nobel Prize in Physics. Thank you so much.
Thank you, sister. Behind every event, a strong, dedicated team is there. Now, I take an opportunity to invite Dr. Hema Subramaniam, coordinator of Sophia Noble Oration, to say a few words. Over to you, Dr. Hema.
Thank you, Meeta. It is our pleasure to welcome you all to the Sophia Nobel series being held online this year. Since its humble beginnings in 2002, initiated by Dr. Arunan, the then head of our department, to celebrate the 25th year of our Department of Life Sciences at Sophia College, it has bloomed to this today. The purpose of such an event has been to bring to a wider audience a flavor of not only the award-winning work, but also the persona of the academicians behind these discoveries and awards. We had started by organizing the Sophia Nobel Oration in Physiology or Medicine and have continued it till date. And so it is now the 19th such oration in that field. And then, after a few years, the Physics and Chemistry Nobel orations also started. And now, this year, we present to you the whole bouquet of physics, chemistry, physiology, medicine, literature, peace, and economic sciences, Sophia Nobel orations, in a series from today onwards up to the 27th of this month, organized by an enthusiastic team of staff and students. The Science Nobel orations are supported by the DBT Star Status Funds, and the Humanities Nobel orations are supported by the RUSA funds. So once again, a warm welcome to each one of you, and do join in for all the talks. I now hand this over to Ms. Meeta Saxena, Head of the Physics Department, for taking over today's event. Thank you. Meeta, over to you.
Thank you, Hema ma'am. Now I hand over to Vidushi to take the session forward and introduce our today's guest speaker. Over to you, Vidushi.
Thank you, ma'am. It is my honor to introduce our guest speaker, Dr. Jasjeet Singh Bagla. He received his doctorate degree from the Inter-University Center for Astronomy and Astrophysics, Pune in 1996. He has been associated with elite institutes like Institute of Astronomy and Harvard Smithsonian Center for Astrophysics in Cambridge and Harish Chandra Research Institute in Allahabad. He is currently working at the Indian Institute of Science Education and Research, Mohali. He has numerous research papers published in reputed journals, and his recent work has been on gravitational clustering, cosmological n-body simulations, and dark energy. Before I invite Dr. Bagla to take over, a gentle reminder for the participants to post their questions in the chat box. Now I would request Sir to deliver his lecture. Over to you, sir.
Thank you very much. And thank you for the very kind introduction and inviting me and giving me an opportunity to interact with the students at your college and the wider audience that you are reaching to. Okay, so we need to get this started. Yeah, I hope you can see my screen. So the Nobel Prize in Physics for 2020 was given to these three people. On the left is Roger Penrose from Oxford. He got half the share of the prize. And Reinhard Genzel, who is in the middle, and Andrea Miyages on the right. So Reinhard Genzel and Andrea Ghez got 1/4 share each of the prize. The prize is divided into two halves, not just in terms of money, but also in terms of the topics and themes. So for Roger Penrose, the award has been given for the discovery that black hole formation is a robust prediction. robust prediction of general theory of relativity. And the other half has been given jointly to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our own galaxy. Notice that for the second half, they do not mention discovery of a black hole, but they are talking about discovery of a supermassive compact object. And I will try to illustrate the difference between these two. It is not just hair splitting, but there is a reason for this. Roger Penrose is an emeritus professor at the University of Oxford. He works in the Department of Mathematics. He trained as a mathematician and graduated from University College London, went on to Cambridge University for doing his PhD on tensor methods in algebraic geometry. And he introduced the use of topology of light cones to study spacetimes. I will talk a little bit about exactly what that means. But before I get there, it is important to get a sense of how this whole idea of black holes has developed over time. Since we are talking about black holes, which are supposed to have a very strong gravitational field, it is pertinent that we start with Newton, who conceptualized gravitation as a universal force in the 17th century. His theory was successful in explaining planetary motions as well as terrestrial phenomena. The great breakthrough of Newton was not just in explaining planetary motions, but in pointing out that the way objects fall on the Earth and the way the moon goes around the Earth is due to exactly the same force. One does not need different rules for phenomena on the Earth and phenomena related to planets and stars and the moon. And that is why it is called a universal force. And he in some sense shattered the old Aristotelian model where one set of rules applied to the Earth and the vicinity, and another set of rules applied to the stars and planets and so on. Now, once Newton gave his theory, people started to analyze implications of gravitational force, and many things were worked out. For example, people realized that the comet Halley, named after Edmund Halley, who figured this out, is a periodic object and visits the inner solar system once in 76 years. The high point, in some sense, was the discovery of Neptune in 1846, as it was predicted. And this was a high point because a theoretician calculated the possible position of a planet which was affecting the orbit of Uranus, which was the outermost planet known at that point of time. And by using very complicated calculations in Newtonian theory of gravity, he figured out where this planet may be. He wrote to an observatory, and the very first attempt, they actually discovered the planet. So at this stage, essentially everyone was in thrall of Newtonian gravitational force and the way the whole thing had been conceptualized. And people took it very, very seriously and wanted to further explore the implications of law of gravitation. The other major input is the speed of light. As you are aware, black holes are defined as objects from where even light cannot escape. And the critical part over there is that light is the fastest thing that we know of. Romer was an astronomer from Denmark, and he was the first person to measure the speed of light. And he did so by observing eclipses of Io, which is a satellite of Jupiter. So he was just timing successive eclipses of Io, and he did that over a long period of time, more than 1 year. And he found that when Earth was moving towards Jupiter, the time between successive eclipses was shorter. And when the Earth was moving away from Jupiter, the time between successive eclipses was longer. And he attributed this to a finite speed of light. It is essentially a kind of Doppler effect. And he used this hypothesis to then calculate the speed of light. He got a number which is not terribly far away from the speed of light as we know it. It was at least the correct order of magnitude. But recall that the speed of light being 3 into 10 to the 8 meters per second is far higher than any other speed that we are accustomed to. So it essentially astonishes anyone, and scientists were also uh, curious about what the effect of gravity on light may be. So one of the conjectures which came up was this was done independently by John Mitchell and Laplace. And what these people did was to try and imagine a star which otherwise would be like the sun, but it is so massive that even light cannot escape. Uh, what John Mitchell did was to just think of a star like the sun, but bigger. If it is bigger, it is more massive. And then he asked, how large should that star be for uh, it to become impossible for even light to escape from it? So this is from his research paper. This is Old English. So S, what we call S today, was written as F, and therefore semi-diameter appears as femi-diameter, and sphere is fear, and sun as fun. What he figured out was that if we have a star like the sun with exactly the same density, but it is 500 times bigger, then in that case, the escape velocity from such an object would be equal to the speed of light. So any object which is even marginally bigger than that would therefore not be visible, because light from such a star would not reach us. He did not stop there. He then asked, suppose such an object exists. If light cannot escape it, how will I see it? How will I figure out that such an object exists? And then he said, while we may not be able to see this object, but we can see the gravitational influence of such an object on things which are around it. So if we can see non-dark stars, so he called this object a dark star, and he said that if there are other luminous objects which are revolving in orbits around a dark star, then by observing the motion of such objects, we can figure out the presence of such dark stars. He and Laplace both went on to say that for all we know, the universe may be full of dark stars, and a lot of matter may be in the form of such objects. But of course, it was speculation based on Newtonian theory of gravity. But this speculation was taken seriously, but there was no observational way, at least at that stage, of verifying such things. Remember that we are talking about a time which is almost 200 years ago. Telescopes were known. Photography had become known, but it was still not, people had not figured out how to take photographs of stars through a telescope. That was something which had to wait for more than 50 years before it became possible. And therefore, it remained a hypothesis which could not be tested. And for the students who have studied basic mechanics, just the formula of escape velocity, which is 2gm by r square root. And if the escape velocity is the speed of light, then the size of such an object would be 2gm by c square. So this formula will appear a few times during the talk. Before any verification of ideas of Mitchell and Laplace could be done, Einstein appeared on the picture about 105 years, 6 years ago, and he proposed his own theory of gravitation, which is called the general theory of relativity. And he said that we need not consider gravity as a force. Instead, gravity is modification of the curvature of space-time in the vicinity of massive objects. And because this space-time is curved, objects which are supposed to move in straight lines tend to move in orbits which are not straight. And Einstein gave the detailed mathematical theory in 1915, of how space-time gets modified due to presence of matter and energy, and how the modification causes deviations from straight lines for paths of any other particle which happens to be there. It was also realized that special relativity is applicable in small regions in freely falling frames. So, for example, if there is if we have an observer inside the space station, because the space station is always falling towards the Earth in its orbit, there is no force over there, and it is a small inertial frame, and that is why astronauts in space station feel weightless. They are not massless, but they feel weightless. It is not because gravity is not there. Gravity is very much there, but because the space station is falling, the effect of gravity is nullified, and it becomes an inertial frame of reference. Soon after Einstein gave his theory, people started working on it, and the first exact solution was worked out by Carl Schwarzschild. He had, at that stage, this is in 1918, he was recovering from an injury at the war front, and while in hospital, he worked out the exact solution. And for simplicity, he assumed that we just have a point mass, and there is spherical symmetry in the gravitational field or curvature of space-time, and things are also independent of time. He found that the solution is singular, and by singularity, what I mean is that physical quantities which you calculate in the theory, they become infinite. So that is not a nice thing. You don't want the quantities which you can measure to become infinite, because that means that either the theory is breaking down or the theory is telling you something which is extremely unusual, and that has to be interpreted. So what Schwarzschild found was that the solution is singular at two places, which is at the center where all the mass is located. And there is also a horizon surrounding the central point, which is at the same radius as the radius for black hole or dark star that we had earlier, where things seem to, some things seem to go to infinity. So at that stage, this is 1918, the understanding was that the gravitational field for a point mass has two sets of singularities. People did not understand it fully, and therefore it remained a mathematical curiosity at best for some time. To give you an idea of numbers, if I have a dark star or a black hole which has the same mass as the sun, then its radius, the radius of the horizon, would be 3 kilometers, which is much, much smaller than the radius of the sun as we know it. If you wanted to have a black hole same mass as the Earth, its radius would be 9 millimeters instead of 6,400 kilometers. That is the radius of the Earth. And because the radius is proportional to the mass, if I increase the mass by a factor of 3, the radius also increases by a factor of 3. Therefore, if I have a mass which is 3 times the mass of the sun, the Schwarzschild radius or the horizon radius is 3 times the horizon radius for the sun. So instead of 3 kilometers, it is 9 kilometers. Another curiosity of Schwarzschild's solution was that unlike Newtonian gravity, in this, light itself can get into a circular orbit around a black hole. And this happens at 3 by 2 times the Schwarzschild radius. So in case of the sun, it will be at 4.5 kilometers, and so on. In fact, it is this radius which we detect when the Event Horizon Telescope imaged the black hole at the center of M87, a nearby galaxy. And that is how the mass of that black hole was reduced. So the key features of Schwarzschild's solution for general theory of relativity, which was the first black hole solution to be known and the only solution which remained known till the early 1960s, was that there is a horizon Nothing can escape from this horizon. Things can fall in. Now we understand it as a one-way membrane. At that stage, the understanding was not so clear. Photons can be in a circular orbit around this object. And unlike Newtonian gravity, where you can have as small or as large an orbit around a massive particle, in this case, the smallest stable circular orbit is at a distance of 6 gm by c squares, which is 3 times the Schwarzschild radius. Another peculiar phenomena which people noticed in Schwarzschild solution was that unlike Newtonian mechanics, even particles with a non-zero angular momentum can fall to the center. When we study mechanics as undergraduates and later, we know that in Newtonian mechanics, anything which has an angular momentum faces a centrifugal barrier, and it cannot fall to zero in gravitational field. Similarly, in electrostatic field, in Coulomb field. However, the effective force in general theory of relativity in the Schwarzschild solution, it does not remain simply as 1 by r square, but it also has higher powers of 1 by r, and therefore it can overcome the centrifugal barrier. Schwarzschild also asked, if I have a star, what will be the gravitational field and what will be the solution? He again assumed spherical symmetry, and he found that for a star like the sun, the solution is not singular. There is no horizon. But because the density distribution inside the star, which Schwarzschild had assumed to be constant, and we know that inside stars the density is not constant and there is pressure, so people did not know what to make of it or whether this kind of a solution applies to real stars or not. So it remained, and as I said, it remained a mathematical curiosity, limited, confined to the 1 or 2 books on general theory of relativity which were written in the early years. The first time when the question arose as to could it have bearing on reality was when Subramanian Chandrasekhar pointed out that white dwarf stars cannot have a mass more than 1.4 times the mass of the sun and be stable. So if you took a white dwarf and keep on adding mass to it somehow, then at this threshold of 1.4 times the mass of the sun, it should no longer exist as a white dwarf star and something will happen. The question was, what will happen? Chandrasekhar would only show that it will no longer be stable and its radius will go to zero. This result was derived by combining special theory of relativity and quantum statistics, which were special relativity at that stage had been around for 25 years, but quantum statistics developed by Fermi and Dirac was less than 4 or 5 years old at that time. So the question remained as to what happens, and Chandrasekhar could not answer it, and it remained an open question. This work was done in early 1930s. The next step was taken by an Indian mathematician, Vishweshwar Dutt. He discovered an analytical solution for collapse of a spherical ball of dust. People who study relativity use the mnemonic dust not for what we normally call dust, but for anything which does not have any pressure. So for something which has no pressure, which is non-relativistic in nature, he asked what will happen if this thing collapses. His own interest was actually in cosmology and an expanding universe, so he was looking at expansion rather than contraction, but the solution was there, and he noted that it will collapse to a point eventually in finite time. This work was published first in 1937, but without any commentary on what it means. Unfortunately, he died in a hernia surgery in 1938, and he could not develop this idea any further. His solution was republished in 1997 as one of the memorable papers, what they call golden oldies, in the journal called General Relativity and Gravitation. A year or two later, Oppenheimer, of the fame of Project Manhattan, where the atomic bomb, nuclear bomb was developed, and his student Schneider, they independently discovered the same solution in 1939. Notice that this is on the eve of the Second World War. And they were able to show that if we take a pressure-free spherical ball of matter and just let it be, it will collapse and it will form a black hole. The question which arose within the community was, yes, it may happen if there is no pressure, but real stars do have pressure, and that is why sun remains in equilibrium. What will happen if there is pressure? Before Oppenheimer and Schneider could address that question, Second World War had started and their attention was drawn in that direction. So here you can see a picture of young Oppenheimer. For almost a decade, nothing much was done in this direction, and people kind of lost interest. Somewhat formal work, but which was very critical to what Roger Penrose did. That work was done by Professor Amal Kumar Rai Chaudhary, working at the Ashutosh College in Calcutta at that time. And he studied what happens when you have an arbitrary distribution of matter and how does it evolve. And he demonstrated that the local behavior in any such arbitrary distribution of matter can be decomposed into convergence or divergence. So the matter is getting compressed or is expanding, rotation, going about an axis, or shear, which is like different sheets within the matter are sliding across each other. And within his work, he was able to demonstrate that for most reasonable materials that we can think of, if we start off with matter distributed over a finite region, even if there is pressure, it will tend to collapse. But his approach again was somewhat mathematical, and he did not dwell on this aspect or try to prove it in a more, what shall I say, more complete manner. And his study was local, whereas the problem of demonstrating that black holes can form required a larger scale understanding of collapse. Nevertheless, his work was extremely critical, and without this work, Roger Penrose could not have taken up any of the calculations that he did later on. So, while black holes had remained in the domain of mathematicians and relativists for a long time, starting with Schwarzschild's solution in the second decade of the last century. In 1960s, suddenly they became of interest for astronomers in general. It happened because an astronomer named Martin Schmidt, working at the Palomar observatories, he found he had been observing objects which he thought corresponded to radio sources that had been detected in a survey at Cambridge. So he was looking at a specific source called 3C273. So 3C means the third Cambridge catalog, 273 is just the number in that catalog corresponding to this source. And he was trying to get spectra of these objects to try and figure out what these things are. Because normally stars do not radiate in so much in radio wavelengths. They emit mostly in optical light and infrared. But this object was first detected in radio, and therefore it seemed to be peculiar. He wanted to know what it was, and he went and took a spectrum. And this redshift of 0.158, which means that wavelengths of all the emission lines were shifted to longer wavelengths by about 16%. This was the largest known redshift at the time. Now the record holder is way beyond this, where the redshift is 11 and the fractional change in redshift is almost 100%. So this was the largest known redshift at the time, and it took him a while to figure out what was going on. And if the redshift was so high in the expanding universe, then this was clearly the furthest object in the universe known at that time. And if it was the furthest object and it was still so bright, then clearly it had to be emitting a huge amount of energy. And a very quick calculation showed that this much of energy cannot be emitted by a star or even by a collection of stars. And therefore, you need something unconventional. And theoretical astrophysicists very quickly came up with the explanation that if matter is falling towards a black holes are the most compact objects, then as it falls, it goes deeper and deeper into the potential well, and therefore it picks up more and more kinetic energy. And if this kinetic energy can be converted into radiation somehow, either through dissipational or frictional forces, which will naturally occur if this material has some amount of angular momentum, then it will form a disk, and different rings in the disk, as they rotate around the center at different rates with different speeds, there will be a friction between them and the matter will heat up. And astronomers figured out that this could be a nice way to account for the high luminosity of this particular source. So then you needed a black hole. But if you needed a black hole, you need to prove that such a black hole can form through astrophysical processes. And therefore, it suddenly became a very relevant astrophysical problem and not just something which is in the domain of mathematicians and relativists. So this is where Penrose entered the field. And he first started working on the Schwarzschild solution, which was given in 1918. And he studied what happens to an object which is falling into a black hole, into the Schwarzschild black hole, and what happens to the light being emitted by such an object. So the first thing he was able to do was to demonstrate that there is no singularity at the horizon. That singularity arose because of the choice of coordinate systems used by Schwarzschild. And if we modify the coordinate system, general theory of relativity allows arbitrary modifications in coordinate systems, and we attach a coordinate system to something which is falling in, then this singularity disappears, but the singularity at the center remains. So this was first step. The second step which he was able to take was to show that all light emitted by an object which is falling in will fall only towards the center of the black hole once it crosses the horizon. So even though there is no singularity, something strange happens over here, and effectively going forward in time becomes equivalent to falling into the black hole. And this is the reason why no light can come out from here. So Penrose published this work in 1964, and he named the coordinates after two relativists, Eddington and Finkelstein. So Eddington had written the first textbook on general theory of relativity, and Finkelstein was also a relativist, but neither of them had published this kind of a work. It appears that they gave a suggestion, and Penrose, given his mathematical abilities, was able to do the calculations which neither of them had been able to do. So Penrose called the horizon as a trapped surface which traps anything which falls into it. Then he went on to generalize this concept, and this is the Nobel Prize winning work. He said that once trapped surfaces form in any space-time, it is inevitable that a singularity will form at the center, which means even though you start with a situation which does not have any black hole or any singularity, material which was there and all the quantities, all physical quantities were finite, if they move in such a way that a trapped surface forms at some stage, it naturally leads to formation of a singularity and a black hole. He used topological constructs with the Raychaudhuri equation to prove this. And the use of topological constructs is what gave a global view, unlike the local view which is there in differential equations of Raychaudhuri. And this is basically it. I cannot go into mathematical details because they are extremely intractable. They are a branch of relativity which very, very few people study, and certainly not for general consumption. Interestingly, just around that time, Roy Kerr had found a second solution for a black hole in general relativity, and this was a rotating black hole, which was also useful because one of the critiques of Schwarzschild solution had been that it has no angular momentum, whereas we do not know of any object in the universe which has zero angular momentum. And Kerr's solution also had trapped surfaces. Uh, so Penrose was able to prove these, but he was not able to show whether formation of trapped surfaces is inevitable in any collapse. That still remains an open problem. And it is a part of what is called the cosmic censorship conjecture. So he showed that if trapped surfaces form, then a singularity will definitely form. But he was not able to prove that if there is a singularity, it is always surrounded by trapped surfaces. Penrose has also made many other very key contributions. One was, of course, even immortalized in movies, generalization of singularity theory to cosmological context and to show that the universe had its beginnings in a singularity. Second is Penrose process, which is that it is possible to extract energy from a rotating black hole, the solution which was given by Roy Kerr. And third, he worked on impossible geometrical constructs like this triangle shown below on the left. In this, he also collaborated with Escher, the famous painter. One other very key contribution was tiling with five-fold symmetry. And this was a purely geometric construct that he came up with. Interestingly, he gave these tiling patterns for five-fold symmetry, which was supposed not to exist till then, in 1950s and 60s. And in 1980s, when quasi-crystals were discovered with a five-fold symmetry, this work was recalled and became a part of standard texts in crystallography. The discovery of quasi-crystals was awarded by a Nobel Prize in chemistry, and many people felt that perhaps Roger Penrose should have been awarded at that time. It would have been interesting to see a mathematician getting a physics and a chemistry Nobel, showing the true interdisciplinarity of science. Now coming to the second part about the so-called black hole in the center of the galaxy. As I said earlier, over here, the citation is that the award has been given for the discovery of a supermassive compact object at the center of our galaxy to Reinhard Genzel, who works in Max Planck Institute of Extraterrestrial Physics, and Andrea Ghez, who works in University of California, Los Angeles. Starting in 1980s, evidence for black holes in centers of galaxies had been growing. And it was known that the mass of the really big black holes at centers of galaxies is correlated with the mass of the bulge in spiral galaxies. So here is a picture graph from a paper in 2004, which shows the bulge mass on the x-axis and the black hole mass on the y-axis. The axes are logarithmic and mass is in the units of mass of the sun. So you can see the leftmost point is actually for our own galaxy, as it was the mass estimate was known at that time. And you can see that observations indicate black holes, presence of black holes of masses anywhere between a few million to a few billion times the mass of the sun. And of course, galaxy mass itself could be anywhere between a billion and a trillion times the mass of the sun. So since this was known, people were curious as to see whether they can find or prove the existence of a black hole at the center of our own galaxy. The main difficulty is that we are sitting in the plane of the galaxy about 25,000 light years away from the center. Now, how do we look at the center? Because within the plane of the galaxy, there is a lot of gas and dust, which is there in between us and the center. And that absorbs and scatters a lot of light. To illustrate this point, I have shown pictures of the entire galaxy taken in different frequencies in different wavebands, starting with radio waves at 408 megahertz at the top and going down to gamma rays at the bottom. Now you will notice that in some wavebands like radio or gamma rays, we can see to the center of the galaxy, but we cannot see the stars. And in other wavebands like optical, we can see the stars, but we cannot see to the center of the galaxy. The only sweet point in this entire set of observations of the galaxy is in the near infrared. This is light which we cannot see with our own eyes, but astronomers can detect it using special cameras. And here we can see the center of the galaxy. We can also see the stars. So this is the waveband which was chosen by Reinhard Genzel, and same band was chosen later by Andrea Ghez. So the idea was you image the center of the galaxy, search for stars near the center, and use observations to infer mass distribution near the center. Unfortunately, scattering due to dust causes a significant reduction in flux, and we receive only about 0.1% of the light from stars at the center of the galaxy. This sounds very little, but it turns out that in other wavebands it is much worse. So the K band, or the 5 micrometer wavelength, which is about 10 times longer than the wavelength which we most comfortably see in yellow, that is the optimal waveband for observing the center of the galaxy. The other difficulty which they faced is due to the turbulent atmosphere. And what this does is, we are familiar with twinkling of stars, which happens because the image of the star keeps on shifting around because of the turbulent atmosphere. And the same problem occurs for astronomers as well. And because they were looking at very faint objects, it was really a serious problem for them. So initially they tried some techniques which worked to some extent, but the real breakthrough came with the implementation of what is called adaptive optics. So if I have a very distant source in the universe, here of course I've shown Saturn, which is not really a distant source, only a few light minutes away. The light from there should come in as plane waves, but because of the turbulent atmosphere, the plane waves get disturbed and become corrugated. Now, anyone who has taken a long distance flight is familiar with the idea that the upper atmosphere has a lot of turbulence. It can make planes shake, but it can also shake up the wavefronts from these distant sources. So what astronomers did, and this took a lot of development, was to implement a system where the wavefront is sensed and corrected so that you again go back to a plane wavefront and you get exquisite images of the sky. And the way this is done is by imaging this, let us say you image a very bright star, not using a single mirror or a lens, but by an array of mirrors or lenses. And because we know that the point source is, there is only one point source, in that case, we know where the image should have been, which is shown by dashed lines on the right. But because of the perturbed wavefront, the image actually forms at a slightly different place. So by looking at displacements of images of point sources, we can figure out how the wavefront is perturbed, and then a correction has to be applied. Next difficulty which people encountered was that every field of view does not have a bright star. So what astronomers did was to create a star of their own. What they do is, by focusing laser in the upper atmosphere, well above the turbulent layer, they create an artificial star in the vicinity of the field which they want to observe, and use the perturbation of the perturbed wavefront from that artificial star to make the corrections. So this picture shows two telescopes of the European Southern Observatories, the very large telescope, and it also shows a laser guide. You can see the large Magellanic Cloud above the left telescope, just above the left telescope. And of course, you can observe the band of the Milky Way over here. So this technique was developed in late 1980s, and first demonstration came in 1989 This is a signed photograph. On the left is photograph of a double star without adaptive optics, and on the right is with adaptive optics. And you can see that on the left, it is impossible to make out any structure, whereas on the right, you can see two stars very, very clearly. So this improved the resolution and it enabled uh, people to make better images. So this demonstration was done at a wavelength of 2.2 micrometers, which is about half of what is typically used for studies of the center of the galaxy. So armed with this technique, these two groups started imaging the center of the galaxy and observing stars. And they found that they could see stars moving around in their orbits over time. I will show you a movie as well. But what is shown on the right over here is the observed positions of a star named S2 over time. The first data point is 1992, which is at the top over here. Then it kind of goes clockwise. 1995 is the second observation. And then there are several observations in between. 2001, by 2001, it has almost done half the orbit. And by 2010, it is back where it was in 1992. Notice that the error bars on observations are continually reducing because they are using bigger telescope and they are using uh, better techniques, improved techniques. Observations are from two telescopes, New Technology Telescope, which was the first one to deploy adaptive optics, and VLT. These are run by the European Southern Observatories, where Reinhard Genzel works. And the red points are from Keck, which is used by Andrea Ghez. Keck is in the Northern Hemisphere, NTT and VLT are in Chile. Keck is in Hawaii. So once you have the orbit, once you are able to figure out orbit of a star, then we can fall back on either Newtonian gravity or weak gravity from Einstein's theory of relativity and figure out how much is the mass contained inside that orbit. So that is the physics bit which goes in. So you can see images taken over a 5-year period. So I will show this movie again. So this shows a stack of images taken over a long period of time. And as we zoom in, one is able to see the motion of a star around the orbit. It completes its orbit. The cross in the middle points to the center where the mass is supposed to be concentrated. Using this, one can figure out how much mass is contained within. If we look at the galaxy at larger scales, then this is the distribution of mass as a function of radius. And you can see that the mass enclosed keeps on going down as we go in. Units are kiloparsecs, something galactic astronomers use quite a lot. 1 kiloparsec, or rather 1 parsec, is 3.26 light years. So the innermost point here, which is at 1 kiloparsec, is at about 3,260 light years. But these observations, of course, take us way inside using orbit of S2 and also orbits of other stars. The shortest time period star that has been discovered and observed is S62, shown in red over here. Combining all of these, one is able to get this enclosed mass as a function of radius. Notice the earlier plot I showed you was in kiloparsecs. Now we are talking about parsecs. So 1 kiloparsecs is 1,000 parsecs. So that plot is way outside. This is on the inside. Work done by Reinhard Genzel and Andrea Ghez has been to discover the S stars. Out of them, the innermost ones are S2 and S62. And you can see that the mass enclosed is now changing with the radius beyond some point. The innermost observation is of S62 in terms of stars, And that gives us a mass, enclosed mass, a little bit more than 4 million times the mass of the sun. If this is indeed the mass, then the event horizon is at the black arrow coming from top. Okay. And that will be at a scale of about a millionth of a parsec. Whereas the stars which we have seen have orbits going in to about 1 by 10,000 of a parsec. So there is still a gap of a factor of about 100. And that is why the Nobel citation talks not of discovery of a black hole at the center of the galaxy, but a demonstration that we have an extremely compact object at the center of our galaxy. The current status is that these people have gone on to measure even gravitational redshift for stars in the vicinity of the central object. They have also seen relativistic corrections to various orbits. And these verify the space-time geometry in the weak field limit as predicted by general theory of relativity. And now they have gone on to doing K-band interferometry with 10-meter class telescopes, and results are likely to improve further in the next decade. So the summary is that the Nobel Prize 2020 recognizes theoretical advancements and observational work that established black holes as astrophysical objects. It also recognizes the observational work which comes close to demonstrating presence of a supermassive black hole at the center of the galaxy. But as I mentioned, it shies away from stating that they have established the presence of black hole. Roy Kerr, thankfully he is still alive and hopefully will remain so for a few years so that he can get his Nobel. And the Event Horizon team, which did the imaging of the center of M87, these two teams, perhaps Roy Kerr and EHT team, perhaps have a stronger claim on establishing presence of a black hole and astrophysically relevant black hole. So I will stop here. Thank you. So I'll be happy to take questions now.
Yes. Thank you, sir, for your wonderful talk. We'll be proceeding with the question answer session. So, our first question for you is, what are neutron stars and what is a magnetron?
Okay. So I had briefly mentioned white dwarf stars in the talk when I talked about Chandrasekhar giving his white dwarf mass limit, Chandrasekhar mass limit. In white dwarf stars, gravitational force is balanced by the repulsion of electrons, not electrostatic repulsion, not Coulombic repulsion, but repulsion caused by the tendency of electrons that two of them cannot be in the same place in the same state. So you are familiar with Pauli exclusion principle. And because of this, there is what is called a degeneracy pressure. And it is because of this pressure that they are able to resist gravitational force. And that is what gives us white dwarf stars. When neutrons follow the same model, same principle, two neutrons are also spin half particles, and they are also fermions. So two neutrons cannot be in the same place. So neutron stars are those objects where the degeneracy pressure of neutrons resists gravitational fall, and it gives us a stable structure. So we have observed neutron stars in the form of pulsars. They emit rotating neutron stars, give out pulses of radiation, typically in radio, but sometimes also in optical and X-rays. And these have been observed. Magnetars are special kinds of pulsars which seem to have a much higher magnetic field than a typical pulsar. I hope that answers the question.
Yes. So, we have the second question, which is, what is on the other end of the black hole?
What is on the other end of the black hole? As I said, at the center of the black hole, there is a singularity, which means that the theory itself breaks down and is unable to make any predictions for what will happen. But that is precisely at the center. If something falls into a black hole, it cannot go anywhere else except the center. So what we know is that if something enters a black hole, falls into a black hole, it keeps on falling until it hits the center. And we can show that this happens in a very short period of time. So there is no other side of the black hole. You inevitably get to the center of the black hole. And unfortunately, our theory stops giving us answers as to what happens there.
Thank you, sir. Sir, our next question is, if a supermassive black hole and a stellar black hole were like supposed to collide, what will happen?
In that case, essentially a slightly larger mass black hole will form. If they collide head-on, then that is what is expected. The collision will give rise to a new black hole, which will undergo some fluctuations and settle down after emitting some gravitational waves.
Okay, sir. And so our next question is, so do you think will our sun ever become a black hole?
Left on its own, no, because the sun is not massive enough. It'll shine like it is shining for another 4.5 billion years, long enough for us to kind of wipe ourselves out. And after that, it will become a giant star, which may engulf Mercury and Venus within it, might even engulf Earth, although that is less likely. After that, it will become a white dwarf star and it will expel the outer atmosphere. It is not massive enough to become a black hole on its own.
Okay, sir. So thank you, sir, for answering our questions. Now I'll be handing over to Marianne to give vote of thanks.
Yes.
Thank you.
Good evening, everyone. Uh, I, Ms. Marianne De Silva, have the honor of proposing the vote of thanks for the first of the prestigious Sapphire Nobel Oration Series 2020-21. I would like to begin by thanking Dr. Bagla for this wonderful and informative session. Thank you for shedding some light into our lack of knowledge of black holes. Thank you, sir. I sincerely thank our principal, Dr. Sister Ananda Amrit Mahal, for encouraging and supporting us. We also like to place on record our thanks for the support extended to us by the DBT status. Lastly, we extend our gratitude to all our participants who are watching us live on YouTube. Before we close, a gentle reminder that the link for the feedback form will be active for 1 hour after we close this session. Thank you.
Thank you. Thank you very much.
Thank you, sir.